Let's continue with some examples of finding eigenvalues, eigenvectors, and eigenspaces. We saw in the last video several examples of how to do this for 2 by 2 matrices. What if we had a 3 by 3 matrix? So here you can see a 3 by 3 matrix A, and we wanted to find eigenvalues. We'd be looking for, again, solutions to the determinant of A minus lambda I equals 0. So in this case, we're looking for the determinant of minus 1 minus lambda minus 2, 2, 4, 9 minus lambda minus 6, 4, 8, minus 5 minus lambda. And so we've got ourselves a 3 by 3 determinant. We saw in an earlier chapter how we could work our way through computing this determinant. And there's, a few different techniques. We could attempt some row reduction, or we could kind of just go through the expansion of this, across a row or down a column. In any case, this is going to get pretty ugly. I mean, we could attempt to, let's say, do our cofactor expansion maybe just across that first row. So let's start to see what this will look like. We might give up here, but let's see. So this would end up being, I guess, -1 minus lambda times the determinant of the 2 by 2 matrix that we get by eliminating the first row in the first column. So that'd be 9 minus lambda, -6, 8, -5 minus lambda. And then moving on to our next one, it's going to be a minus, and then we have a -2. So a +2 times the determinant of the 2 by 2 matrix we get by eliminating the first row in the second column. So 4, -6, 4, -5 minus lambda, and then I guess plus minus plus, so +2 times the determinant of 4, 9 minus lambda, 4, 8. And now we've got a bunch of 2 by 2 determinants. So maybe we'll power through. Let's see. So look for some space. Maybe I'll kind of come up here in the top right of the page. So come up here. All right, so this first one's going to end up looking like -1 minus lambda times 9 minus lambda minus 5 minus lambda, and then a -8 minus 6 times -6, so a plus 48. Okay, and then a +2 times 4 times -5 minus lambda plus 24, and then a +2 times 32 minus 4 times 9 minus lambda. Okay, and then, there's still a bunch more work to do. We'd have to, maybe expand this out and add the 48, and then distribute this in. That would give us sort of that term. And then we'd multiply this, add the 24, multiply by this 2, multiply this through, and then we have our 32, multiply that by a 2. We'd combine all of these. This would lead us to a cubic polynomial. We could then set that cubic polynomial equal to 0 and, attempt to find those solutions. You may have worked on in a previous course, sort of, guessing at one of those roots and then doing some polynomial long division, getting it down to a quadratic, and then, solving from there. You could, depending on the final form of this, be able to factor it in some clever way. There are some other ways. There's even, we have a quadratic formula. There's even a cubic formula, although I don't want to get into that. Very, very complicated. Not something that, you really can just sort of pull out as a tool to be used on the fly. So, there's still a lot more to do. And even once we get this kind of to its cubic polynomial form, there's even more to do. And we might need to, at some point, along this road, turn to a computer or a calculator to help us out. I think I'm gonna sort of skip the steps of trying to simplify this, get that cubic, and attempt to solve that cubic equation there, and just jump right to the computer at this stage and have it help us out. I want to come over here to our book actually. So our book includes in this section activity 4.2.4, excuse me, in sort of section 4.2.4, activity 4.2.5, which has the different ways we can use Sage to find eigenvalues and eigenvectors. There's not really a built-in way in like your graphing calculator or that linear algebra toolkit I've shown you to find eigenvalues and eigenvectors. Wolfram Alpha is a tool that you might be familiar with that is free and available online that can do this. Sage, of course, I'm about to show you in your book, and a lot of sort of coding languages, Python and the like, MATLAB, sort of Mathematica proper, not just Wolfram Alpha, will have the ability to do this. But Sage is free and available right here in our book, so I'm just going to take advantage of that. You could see the examples they work through are 2x2 examples, which you could certainly practice with. I'm going to take our 3x3 example, so I have it sort of ready to go here. If I replace their matrix with our 3x3, so you put 3 and 3, and then kind of list out all of the numbers as you go across each row, then there's a few different things you can do. So this first Sage cell is set up to find us the characteristic polynomial in the variable lambda. So we evaluate that. And you can see, this is what we would have landed on if we had gone through all that work I was just describing, this cubic polynomial. And again, now we're at a step, we'd be at a step. If we went through all that work, simplified it all the way down to this, we'd be at the step of, okay, I need to now find the roots of this thing. So a variety of ways you might have done that in an algebra class. Let's come down here. So this next one, if we run this, will give us the factored form of that characteristic polynomial. A little bit nicer, right? So we could see actually immediately that this factors pretty nicely lambda minus 3, lambda minus 1, and lambda plus 1. And so, we could hopefully at this stage pretty easily pick out that the roots of that polynomial are going to be 3, 1, and minus 1, and therefore those are our eigenvalues. But why stop there? We can actually have Sage just tell us the eigenvalues directly. And so, there they are, 3, 1, and minus 1. And then, once we have our eigenvalues, we can go back and find each of the eigenspaces. Let's try this for one of these. So maybe I'll just take lambda equals 3. So let's jump back to our slides. Okay, and so let me erase a lot of this. So we just discovered that lambda equals 1, minus 1, and 3. Hooray! So those are our eigenvalues. But let's try and find, maybe some eigenvectors in an eigenspace for at least one of these. So give ourselves a little bit of room here. Okay, so all right, so coming up over here, let's go with lambda equals 3. So we want to now find E sub 3, the eigenspace that corresponds to lambda equals 3. So we would want to look at A minus 3i. So that'll be a minus 1, minus 3. It's going to be a minus 4, minus 2, 2, and then 4, 6, minus 6, and 4, 8, minus 8. We're going to augment that with the 0 vector, okay? And now we can do our row reduction. You might be immediately picking up on some things we can do, all right? I might just sort of jump ahead to the reduced or echelon form of this. So again, if you were to row reduce this by hand, go through our algorithm, you would, find that this had infinitely many solutions, okay? And let me just take a second here. Or reduce this with my computer. Okay, so the reducer echelon form of this matrix A is going to ultimately be nice actually, 1, 0, 0. This probably wouldn't have been so bad to do by hand. 0, 1, -1, and then 0, 0, 0. Okay. All right, so what does this tell us? If we were to maybe take our eigenvector to have elements x1, x2, and x3, we see that x1 actually has to equal 0. x3, so we have these two pivots, right? So x3 is a free variable. x1 would be 0, x2 would just equal x3, and x3 is our free variable, so that would also equal x3. And so any vectors in E sub 3 here would be in the span of, I guess, 0, 1, 1, if we just set x3 to be 1. And we could play this same game with lambda equals 1, lambda equals -1, and we would find this. Let's go back to our book, and we will jump down actually to the next box, because the next box actually gives us eigenvectors. So if I were to plug our matrix in here and run this, so you can actually see sort of the form. It gives us eigenvectors right. So those are the ones we want for this class. Those are the right eigenvectors. And there are left eigenvectors, but we're going to be focusing on the right eigenvectors. So we have 3 is the eigenvalue, and 0, 1, 1 is the corresponding eigenvector. That's actually what we just discovered a minute ago. This 1 here tells us the multiplicity of that eigenvalue. So the fact that, scroll up a little bit, this lambda -3 only appeared as a factor, raised to the 1 power. There wasn't multiples of those. Tells us, and again, 3 only appears once in this list. That means that 3 is multiplicity 1. If we were to go through the process of finding the eigenvectors for 1 and -1, we would find them as these other two. So let's look at a couple more examples. Switch back to the slides. Right, so here's another example, another doozy. Actually, it looks a little bit scarier even than this previous one. So just imagine going through looking for, the roots of the determinant of a minus lambda I for this one. Okay, who knows? Maybe all these numbers would come together in some special way, and this would simplify down really nicely. But just on the surface, this looks like, okay, we got lots of negatives, some big numbers, not a 1 or a 0 in sight, right? So a lot going on. So I want to kind of immediately turn to the computer. Although, if it's a rainy day and you're bored, by all means, this is not beyond someone that's in this class's sort of algebraic capabilities. You can, and I've definitely wasted some time playing around with, searching for eigenvalues and eigenvectors of 3 by 3 matrices that look like this, right? And so you can fill a whiteboard pretty quickly doing that. But for our purposes, it's really just hopefully you get the idea. We're looking for the roots of the determinant of a minus lambda I. The nitty gritty we can sort of leave to either the computer, or if you're in the mood to do it, you can do it. So let's jump back to the computer and take a look at this one. So scroll back up. Now, we can maybe skip a few of these. So let's look at that factored form of the characteristic polynomial. So let's go ahead and replace that. So this is this, 9 minus 12, 2, so on and so forth. And let's evaluate that. So you can actually see here that the factored form of the characteristic polynomial in this one would be lambda plus 2 times lambda minus 1 squared. So this squared here tells us that lambda equals 1 is going to be an eigenvalue of multiplicity 2. So something interesting there. And then we'll maybe look at the eigenvalues. I guess this will be pretty much the same thing we just saw, though it's nice to see that 1 showing up twice. So -2, 1, 1. And then the eigenvectors. Okay, so -2, here's an eigenvector. They do have a fraction in here, so you might multiply this by 2 to get rid of that, but in any case, we have that. And then here is an eigenvector that corresponds to the eigenvalue 1. One thing to really note here is that the multiplicity of this is 2, but they're only showing us a single eigenvector. And really what this is telling us is that this is going to ultimately show us a basis for the eigenspace. Excuse me. And so the dimension of the eigenspace corresponding to lambda equals 1 in this example is only 1, whereas the multiplicity of this eigenvalue is 2. Something to take note of that we'll explore further in the next set of videos. But yeah, something interesting there. Let's do one more example. So jumping back to the slides, that was that example. So this one, okay, this one maybe wouldn't be as bad. I see ones and twos and a bunch of zeros. So we could probably go through this one by hand, but just to save a little bit of time, let's go back and do this one on the computer as well. So plug this one in and start with that factored form just to take a look. This one, lambda minus 3 and then lambda minus 2 squared. Again, we've got a multiplicity 2 factor. And then we can plug that in here. Again, 3, 2, 2, and repeats. And then come down here. So this time 3 has an eigenvector 1, 1, 1. Okay, and so a basis for the eigenspace there just with one vector. 2, we can see actually 2 vectors listed. So these are going to be 2 linearly independent vectors that span the eigenspace corresponding with lambda equals 2, and therefore be a basis for that eigenspace. So this eigenspace is dimension 2, and the multiplicity was 2. Compare that to our last example, where we had a multiplicity 2 eigenvalue, but its corresponding eigenspace was dimension 1. Again, just something to sort of take note of. I'm not going to go into why we are so interested in that particular situation in this video, but something definitely to take note of. Okay, so just to sort of wrap things up for this video, a little overview of how we actually go about finding eigenvalues and eigenvectors. So we find eigenvalues by solving this determinant of a minus lambda I equals 0 equation. This is going to be a polynomial equation in lambda, and it's going to have, the polynomial, the characteristic polynomial that appears in this equation will have degree equal to the, if A is an n by n matrix, then it will have degree n. So 2 by 2 matrices will involve a quadratic, 3 by 3 a cubic, so on and so forth. And then step 2, for each eigenvalue, we solve a minus lambda I times v equals 0. So, we're looking for specifically non-zero vectors in that, that solve that homogeneous equation. And the eigenspace associated with lambda is denoted E sub lambda, that is the null space of A minus lambda I. And just like a quick note and reminder here, if lambda is an eigenvalue, then A minus lambda I is not invertible, since then, the determinant of A minus lambda I is 0. Therefore, A minus lambda I must have at least one row without a pivot position. So a quick check, if you row reduce A minus lambda I, and you get the identity matrix, and then you've made an error. That error could be in your steps for finding lambda, right? That's probably the most likely that you've just made a mistake finding lambda. But if you're pretty sure you found the correct lambda, then go back, see if did you plug it in when you did that A minus lambda I part to sort of row reduce? Did you plug it in wrong? Did you row reduce wrong? Right. So somewhere along the way you made a mistake. If A minus lambda I is row equivalent to the identity matrix. So something just to keep in mind, and always nice to have sort of little checks in some of these more complicated problems to see if we've done something right. If you do get the identity, then you just need to sort of go back and check your work. If you don't get the identity right, then that's a good indication that you've done this correctly.